Now let's look at the Bayesian theorem. Before starting the Bayesian theorem, we have to explain some of the concepts here. Let's take a sample space, and let's say this sample space has three subsets, and they're disjoint. Let's say this is A1, this is A2, and this is A3. And it might be more than this. So this AI and AJs, they have this property. They're disjoint, so they're mutually exclusive. Let's assume they're mutually exclusive. It means their intersection is empty set. And we have the other thing. Their union is making the sample space, and which means the sum, since they're disjoint, we can add the probabilities because they're disjoint, and their sum of the sum of their probabilities is equal to basically 1. So you can say the probability of AJs or 1. So this is, we also say this is we mean they're exhaustive. So they cover all the space, all the sample space. Their union covers all the sample space. So we say AJs or AIs are exhaustive. So when we say exhaustive, you understand it covers all. So their union is equal to the sample space. Now, and we take, let's say, as an event. So let's take this is our event B here. So as you see, it has an intersection with A1 and with A2, with A3. So you can say this is A intersection B1, A1, A1 intersection B, A2 intersection B, and A3 intersection B. Now let's keep them in your mind and try to see what happens in the Bayesian. Now, one. We have a collection of n mutually exclusive and exhaustive events. So here is for n equal to 3. This is the case, you understand. Now, for any b, event b, the following equalities hold. The probability of b is equal to the sum of the probability of b intersection a1 up to the probability of b intersection an. So here we are talking about these little intersections here. They're disjoint. So for this reason, their probabilities, their sum of the probabilities will give you the probability of B. And now, since this intersection means B, A, and A1, we can use the conditional probability rule, the multiplication rule for B, A, and 1. So basically, we will have, for this one, we'll have this multiplication from the multiplication rule. This is, you can take it as n intersection or n, same thing. So we'll have this one, and for the others, we will have the same thing. So we can write the probability of B as the probability of A1 times the probability of B, given that A1, and up to the sum of all this type of probabilities up to AN. Now, and also we can write for any event A1, given that B, the probability of AI, given that B, can be written as, using the conditional probability formula, the probability of A1 and B divided by the probability of B. We can write this one as in multiplication rule. By using the multiplication rule, you can write this one, and the from 2, you can also substitute this formula here, and you get a huge formula here. The probability AI, given that B is equal to the probability AI times the probability of B, given that AI, and divided by the sum of all the products of probability of AJ times the probability of B, given AJ. Now, this is the general rule. So for if we take n equal to 2, we'll get the following Bayesian rule. Now, if A1 and A2 are exclusive and exhaustive, they're mutually exclusive and exhaustive, then we have the following. The probability of B can be written, as the probability of A1 times the probability of B given that A1 plus the probability of A2 times the probability of B given that A2. And we can write the probability of A1 divided by the probability of A1 given that B is equal to this. So I'm applying this rule here, and we are applying the same rule for A1 and A2, and we get this result here. Now let's try to, okay, for now we will generally concentrate on the examples with two mutually exclusive sets, but in general you can use for any number of mutually exclusive and exhaustive events. Let's look at this example and try to use the Bayesian theorem. Try to see how the Bayesian theorem used. The store sells TVs from only two companies, 40% from the company A1 and 60% from the company A2. It is observed that 5% of the TVs from company A1 have a defect, and 3% of the TVs from company A2 have a defect. If a customer buys a defective TV, what's the probability that it comes from A1? Now let's try to list what is given to us. So there are some events here. One is, let's say this is A sub 1, and let's define it. Okay, the event that TV is from A1. And the other event is TV is from A2, the company A2, sorry, the company A1. And D, let's say TV is defective. Defective means has a defect. Now, what is given to us? Let's try to write from here this the probability. Okay, 40%. If you buy a TV, it's the since the 40% of the TVs are from A1, the probability that it will be from A1 is 0.4, and 60% is A2, so the probability of A2 is 0.6. And it's observed that 5% of the TVs from company A1 has a defect. So how can you write this one in terms of probability? This is indeed, it's saying what's the percentage of defective TVs among A1? It exactly gives this one, so it will be 0.055%. So you can write the other one also as a conditional probability. If you buy a TV from A2, what's the probability that it's defective? Or you can also use this one here. We know that 3% of the TVs from company A2 has a defect, so it will be 0.03. Now we have them, and let's check some of the things. First, A1 and A2, they don't have anything in common because a TV only belongs to one company, so they have no common TVs, and we say they are mutually exclusive. The first condition satisfied, the mutually exclusive. So this is satisfied. And the second thing is, do they cover all the probable? They're exhaustive. So when you look at them, the PA1, PA2 is equal to 1. So they cover all the possibilities, A1 and A2, all the cases. Now what is asked? What's the problem? So if you buy a defective TV, it means you already know the TV is defective. What is the probability that it comes from A1? So this is the situation now. Now you can write this one. Okay, I will write it here. Now P1 given it's defective. So if you use the conditional probability rule, it will be just A1, PA1, and D divided by probability of D. Now, the probability of D can be written in terms of these. So basically, that will be PA1 times the probability of D given that A1 plus the probability A2 times the probability D given that A2. And for this one, we can use also the multiplication rule. I mean, I'm using the rules here, but you can directly refer to the Bayesian theorem, and it will be the probability of A1 times the probability of D given that A1. So these are given to us. This is given, and these are given, these are given, these are given. And you can put all of them in the formula A1 0.4. And how about this part here? The probability of D given A2 is 0.03. And we have the same thing here, plus the probability of A2, which is 0.6, times the probability of D given A2, which is 0. Okay, sorry, I made a mistake here. This is 0.5. Here's 0.5, and this is 0.03. So, okay, this is the answer, so I will put it here. So it is 0.20, is it, no, is it 0.020 divided by, this is 0.020 plus this one here, it's 6 times 3, it's 18, so 0.018. So this will give you 0.02 divided by 0.038. So this is the probability. You can find the value of it. Now let's look at this exercise. A study has shown that 70% of the people living in a city suffer from lung cancer. Of those having lung cancer, 90% are smokers, and of those not having lung cancer, 25.3% are smokers. If a smoker is selected randomly, what's the probability that he has lung cancer? Now, there are two things here, having lung cancer and being a smoker. So I will say LC is the lung cancer. So a person has a lung cancer. So this is the event that a person has lung cancer. And S is a person is a smoker. Now, what is given to us? Let's try to write. So the probability, it says 7% of the people living in the city suffer from the lung cancer. So it means what if you choose a person here, the probability that he has lung cancer is 0.07. And of those who have lung cancer, 90% are smokers. So this one is saying among the lung cancer guys, among the lung cancer patients, the smokers are making the 90% of them, so which makes 0.9. Now, another information here is of those not having lung cancer are smokers. So of those not having lung cancer, so among the not lung cancer patients, among the people who doesn't have lung cancer, 25% is smoker. So the probability that he's a smoker, given that he's not lung cancer, it's 0.25 to 253. Now, the question is this. So here, these are the given, and the question is, if a smoker is selected, what's the probability that he has lung cancer? So if it is, we know that the selected guy is a smoker. So the condition is the being smoker. What's the probability that he has lung cancer? So this is the question now. Now, in finding this question, let's go one by one. I will try to give you a solution does not directly depend on the formulas. I will try to go with the reasoning. The conditional probability of lung cancer given that smoker, you can write this one as using the conditional probability rule. This is the probability of a person with lung cancer and smoker divided by this person, the probability of being smoker. Now the question here is, how can we find this one? What is the probability that a person is lung cancer and a smoker? So we can write it this way. We can use this one here. These two are given. So by using the multiplication rule, we can say this is equal to the probability that S given that LC times the probability of LC, and this is, we know this is 0.9, and this is 0.07. So this gives you 0.063. Now we are done with this. So this has to be 0.063. So when it comes to, okay, here is the question, what is the probability of being smoker? So here we can use, okay, we can use a formula from the Bayesian. And the Bayesian, if you remember, there was the probability of A1 times the probability of S A1 plus the probability of A2 times S A2. If A1 and A2 have this properties, this mutually exclusive, and we know this A union B will be, okay, the probability A1 plus the probability of A2 will be equal to 1. So it will be exhaustive. So this is coming from the Bayesian. Here, what is A1 in this question? What is A2 in this question? So we want something, two things, two events that are mutually exclusive. They don't have anything in common, and their sum, the sum of their probabilities is equal to 1. In this question, and when we look at what is given to us, LC is given, and there's not LC is here. So in this case, the best choice here is to choose A1 and A2 to be LC and not LC. So obviously they're mutually exclusive, and also the sum of their probabilities is equal to 1. So we choose A1 and A2 this way in the Bayesian theorem. And we can write this as PLC times the probability S given LC plus the probability of not LC times the probability S given not LC. Now, do we know some of them? Okay, do we know them? The probability of LC is 0.07, and the probability that S given LC is 0.9 plus. What is the probability that the person is not lung cancer? So the probability of not LC is equal to 1 minus probability of LC. So it will be 1 minus 0.07, which is 0.93. So then you can substitute this one in here. So this has to 0.93 times what is the probability that S given that not LC, and it's given here. This is 0.253. If you calculate this one, this will give you 0.298. Now we can write this one in here, substitute them. Okay, this was 0.063 divided by 0.298. So this is the probability, and it's equal to 0.211. Now we'll talk about the probability of an at least and at most. The events involving at least and at most. In some questions, we have the probability of at least this and at most this. Now, at least means the minimum, and at most means the maximum. The relation between the probabilities of at least and most is this. Getting at least k plus 1 success, let's say, is equal to 1 minus getting at most k success. Or if you, okay, because they're kind of opposite of each other. So, and we use the complement here because we use getting at least k plus 1 means k plus 1 means not getting at most k. So this is why we have this 1 minus, because they're complement of each other. So if you set a k equal to 0, then you get this result, and this is the probability of getting at least 1 is equal to 1 minus the probability of getting none. So because they're complement events here, so they're complement of each. They're complement of each. So let's look at this question here. A coin is tossed 6 times. The probability of getting at least one head. So what's the probability of getting at least one head? If you try to count all the possibilities here, there are lots of possibilities. So instead of this one, it's better to think about its complement. So getting at least one head. What is its opposite or not? Its negation is getting no head. So you can say the probability of getting at least one head is equal to 1 minus getting no head. Now this is easy to calculate. This is easy to calculate, and it's easier than this one because in this one you have to go, if it is H T H H T T, you have to count all the sample space. Now when it comes to here, what is getting no head mean? What does getting no head mean? And getting no head means getting all tail. So how many tails? It means 6 tails. So what is the probability? They're independent events, so you can say it will be 6 tails, the probability of getting tail, the probability of getting tail, the probability of getting tail. So you can write it 6 times. 1, 2, 3, 4, 5, 6 for each tossing. So this will be 1 over 2 to the 6th power. So you can say this is equal to now, this is equal to 1 minus 1 over 2 to the 6th is 64. So you can say it will be 63 over 64. So let me write here, this is 1 over 64. So this is how we calculate getting at least one head. Okay, let me show you. Yeah. Now, the other question is about probability of getting at most 5 heads. So getting at most 5 head means so getting at most 5 heads. So what is its opposite? So its opposite is at most 5 head means, okay, we will not have 6 heads. So it will be, okay, basically it means 1 minus probability of getting 6 heads. So at most 5 head means not getting 6 heads. So we can write it as a complement. So it will be 1 minus getting 6 heads is it's the same as before. We'll have 1 over 2 to the 6th. So it will be 1 minus 1 over 64, which is 63 over 64. Okay, let's see how it goes in the slide. So complementary events, so we will get this one. Now let's look at this example. The likelihood means like probability. You can take it as probability. The probability that Zahra gets scholarship is 0.7, and Nilf will obtain the scholarship is 0.6. Find the probability that at least one of them obtains the scholarship. So at least one of them. So it says like the probability that Zahra gets the scholarship 0.7. I will say Zahra here 0.7, and Nuf will obtain it is equal to 0.6. What is the probability that at least one of them obtains? So it means Zahra or Nuf will get it. So we can use the complement of this, like the complement of this one will be 1 minus not Zahra and not Nuf. So how can you find the probability not Zahra and not Nuf? So how can you get this one? So since we have an and we assume that they're getting the scholarship is independent of each other, so then it will be the probability of not Zahra. So we assume this is independent here, independent events. So if you remember in the independent events, we have the multiplication rule. So here comes not Zahra and not Nuf. So probability that Zahra will not get it is 0.3 then. So you see, and the probability that not move, it's 0.4. So we can write it as 1 minus, okay, no, this is 0.3 times 0.4, which makes 0.12. So this will give you 1 minus 0.12, which is 0.88. Let's see how it is given in the slides. Yeah, it's the same. And let's look at this exercise. An urn contains 5 red balls and 8 black balls. If 3 balls are selected randomly with replacement, okay, here is important information here. With replacement means you put the ball back. So we put the ball back. So, or the ball is put back each time. What is the probability that there's at least one black ball? So now we are choosing, okay, the probability that 3 balls here, we draw 3 balls and at least one ball is black. Okay, counting the probabilities will take a long time because we have to say first ball, the second ball, the third ball, and it will take time. So instead we can think of its complement. What is the complement of this? At least one black, one is black, means none of them is black. So it means no black. So this is okay. It's complement. So I'm thinking of its complement. So complement means its opposite. So its complement is none of them is black or no black. So then we can write here 1 minus no black. So then now you can calculate no black. No black means it will be all red. So it will be just 1. So 3 reds. So it will be just 3 reds. Now 3 reds, and each time there's the replacement. Replacement makes the drawings are independent. So the drawings are independent. So if they're independent, so we can use this rule here. It will be the probability of red, same each time. So it's because of the independence. So this will be 1 minus. The probability of red is 5 over 13. So it will be 5 over 13 cubed. You can find the result with a calculator. Okay, now what's the probability that there are at most 2 red balls? So let's do the second one. So again, the draws are independent because of the replacement. And what's the probability that there are at most 2 red balls? So at most 2 red balls means what? At most 2 red balls. Okay, what does this mean? at most two red balls means it will be just one ball or two balls or zero balls. Or if you think of its complement, it will be its complement here. At least three balls. But in any case, we have to count all the probabilities here. No, okay, this is good because at least three balls are red. Okay, so at most two red balls means its complement is so opposite is at least three balls red. So here then we can write this is 1 minus the probability that at least we have three red balls. But the at least here is unnecessary because we already have only three balls. So three balls selected, it means we have three red balls. This will be 1 minus, and their independent rows are independent and they don't affect each other. So it will be the probability of red, the first one, the second one, and the third one. And again, it will be 1 minus 5 over 13 cubed. And this is the answer. Lecture 9. Question 1. A coin is tossed 7 times. The probability of getting at least one head is what? Now we can use the shortcut here about the at least questions. Okay, getting at least one head. So 7 tosses. There are 7 tosses. And getting at least one head. At least one head. If we think of its complement, so its complement will be, the complement is, its complement or opposite will be no head. So its complement is, or negation is no head. So we can say this is 1 minus the probability of having no head. So no head in 7 tosses means, okay, no head means 7 tails. So it means this one here, 1 minus the probability of 7 tails. So each toss is independent of each other. So now you can write this one as it's the probability of getting one tail times the probability of getting another tail, and we can write it this way up to 7. So it will be 7 tosses here. So this will be just 1 minus probability of a tail, the 7th power, which is 1 minus 1 over 2 to the 2nd power, so which is 127 over 28. So this will be C. Now, at the convention, there are 7 mathematics instructors and 5 computer science instructors and 3 statistics instructors and 4 science instructors. If an instructor is selected, find the probability of getting a science or statistics instructor. So I will just write all of them in terms of the names of the courses. So the probability getting a science or statistics, I will say science or statistics. So what is the probability of it? So if you look at the union, the OR, we have the addition of the rule. The rule is the probability of science plus the probability statistics. and minus the probability science and statistics. Now, what is the probability of science? So the probability of science is the number of science teachers divided by, so the probability of science will be equal to the number of all instructors, science instructors divided by all instructors. So it will be 4 divided by 7 plus 5 plus 3, 15 plus 4, 19. So it has to be 4 over 19 here. And then plus the statistics here, the statistics, the probability that the teacher is statistics anyway. It's equal to the number of the statistics teachers, 3 divided by 19. We will have 3 over 19. When it comes to science and statistics, a teacher here is not teaching both. So if it's they're mutually exclusive, or we can say a teacher cannot be both, like science and statistics at the same time. So this is just 0. So the answer is 7 over 19. Coin is tossed 7 times. The probability that all 7 tosses are heads. Okay, now the question is the first will be 7. The first will be head. The second will be head. And the 7th will be head. And each time, these are independent events. Each toss is independent. Each toss is independent of each other, so it's not affecting the other one. So you can directly write this one as this. What's the probability of getting the first head times the probability of head for 7 times here? That will be the probability of head, the 7th power, which is 1 over 2 to the 7th, so it has to be 1 over 128. Now let's look at this question. The probability A is given as 0.4, the probability of B is given 0.2, the probability of A and B is given 0.1, and the probability of A given that B, the conditional probability, is asked. So if you remember the conditional probability, the probability of A given that B is equal to the probability of A and B divided by the probability of B. And the probability of A and B is 0.1 and the probability of B is 0.2. If you do this calculation, you will get it 0.5. So this is a direct use of conditional probability formula. Now, 2 events ED are independent and PD is 0.6 and PD and E is 0.28. What's PE? Now let's look at the multiplication rules. Multiplication rule for independent events. If you remember, so multiplication, when it comes to multiplication, think of A and, okay, so it will be E and D, okay? So multiplication, we have this and issue. Now, according to the multiplication rule, what is it? E and D or D and E same. Okay, what is this equal to? If they're independent events, it will be just the probability of D times probability of E. Now, let's use this here. The probability of D and E is 0.28, and the probability of D is 0.6 times the probability of E. And it's not given to us, so we have to find it. So the probability of E, if you divide both sides with 0.6, we'll get 0.28 divided by 0.6. And which is equal to something like 7 over 15, and which corresponds to 0.47. Now let A, B be events with probability A or B is equal to 0.75 and the probability of B is 0.6. If A and B are mutually exclusive, find the probability of A. Now this is given to us, let's write it. The probability of A or B is equal to 0.75 and probability of B is equal to 0.6. And let's write the formula here. The general formula for A or B is equal to the probability of A, so the addition rule, probability of B minus probability of A intersection for A and B. So here it says A and B are mutually exclusive. It means, okay, this one here, this A and B are mutually exclusive. This is also given to us. It means the probability of A intersection B or A and B is equal to 0. So for this reason, you can say this is 0, and now 0.75 is equal to 0. So the probability of A plus 0.6. So if you solve this one, the probability of A turns out to be 0.15. Now, if A and 2 are independent events where the probability of A is 0.5 and the probability of B is 0.2, then what is the probability of A or B? Now, again, we have to use the addition rule here. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Now, we know that one, this is 0.5 and this is 0.2, but the question here is this one. So we know A and B are independent events. So if they're independent, if you remember the multiplication rule, P A and B is equal to PA times PB. So this gives you then, this part has to be 0.5 times 0.2. And if you do this calculation, you will end up with 0.6. So this one here, it's equal to 0.6. A virus has infected 1.8 of a population. A test detects this virus 90% of the time when it is present. So this is an important sentence. It says when it is present, it's 95%, it's positive. It returns false positive. False positive means like it shows positive, but the virus is not present. So 3% of the time it shows a false positive when the virus is not present. If a person selected at random from this population tests positive for the virus, what's the probability that this person is actually infected? So here we have two issues here. One is being infected, so I will write here infected, and this means a person, this is the event that a person is really infected. And I will use tested positive, TP. Okay, for this one I will just say TP or positive. Okay, when tested positive, I will say P. P. Okay, let's say this is I. So it means the event that the person tested positive. There's a difference between testing positive and really infected. So there might be a mistake in the test. So even it's tested positive, sometimes you might not be infected. Now let's have them in our mind. Let's keep them in our mind. So let's try to write what is given to us. The probability, okay, a virus has infected 1.8% of the population. So the probability that a person is infected, so it's 1.8 over 100. but a test detects this virus 95% of the time when it is present. So this is giving you a conditional probability. It says tests detect this virus, so test makes positive, test gives positive. Indeed, when it is present, so if someone is infected, the testing positive, the probability of testing positive, it is 95%. And it says it returns a false positive of the 3% of time when the virus is not present. So here we know that it's not infected. If someone is not infected, then the test is showing positive only 3% of the time. So if a person is selected at random from this population test is positive for the virus, so we know this guy is tested positive. What's the probability that this person is actually infected? So we are trying to find this information here. Now let's try to use the Bayesian rule, but first let's go with the conditional probability rule. So as we know, this is the conditional probability is equal to the probability of I and TP divided by the probability of TP. So now the question is, so we have to find this one and we have to find this one. They're not given to us. Now, how can we find the probability of I infected and tested positive? Now, how can we find it? So we can use the multiplication rule here. If you remember the multiplication rule, this will be, okay, you can write this one as the probability of tested positive times the probability I given tested positive, or the probability that the person is tested, infected, sorry, and the probability that the test is positive and he is infected. So we can use both, we can use both for this. But here, when we look at these, which one is better here? We have this one and we have this one. So it's better, okay, we use the second one. So no need to use the first one here. So the probability that this guy is infected is 1.8% times the probability that the test result is positive, given that the person is infected, it's 95 over 100. So this gives us the probability that the person is infected and the test is positive. So we can write here this one. .8 over 100 times 95 over 100. Now the other thing is about the probability that the person tested positive. Now how can we find the probability, this probability, by using these? Now I will remind you the Bayesian rule here. In the Bayesian rule, you can write probability of TP as A1 times the probability of A1 times the probability that TP A1 plus probability of A2 times probability TP over A2. Here A1 and A2 should be, A1 and A2 should be, they're mutually exclusive, so their intersection is empty set, and also their union or their sum of their probabilities is equal to 1, so it has to be exhaustive. We need this A1 and A2, and what can it be? Here, if you look at here, we have I and not I. You know, this I and not I are clearly mutually exclusive and exhaustive, so we can choose A1 as I and A2 as not I. Then everything will be clear. Then the probability that the test result is positive, the probability of I times the probability that the test result is positive given that the person is infected, plus person not infected times the probability that the test result is positive given that he is not infected. Now we can write this one then. Now what is the PI, the probability? So the probability of TP is, PI is 1.8 over 100 times the probability of test positive, given that the person is infected, so it has to be 95 over 100. Okay, it is this one now, plus not I. What is not I? We can, since this is the complement of I, we can have here 1 minus 1.8 over 100, so which makes 98.2 divided by 100. So this has to be 98.2 over 100 times. So what is the probability, the conditional probability that test is positive given that the person is not infected? It's here, 3 over, I will just in parentheses, I will put them in parentheses, times 3 over 100. Now we have this one now, and then we can write this one here. It will be 1.8 times 95 plus 98.2 times 3 divided by 10,000, and this will give us 0.37. So if you calculate this one, if you do this calculation, you will get this one B. A flashlight battery has 8 batteries and 3 of them are dead. If two batteries are selected without replacement, okay, this is an important phrase here, without replacement. So you take one battery out and you don't put it back, so no putting back, and test it. So 2 batteries are selected, 1, 2, and we don't put them back. So what's the probability that both are dead? So you can say this one, the first battery, that you want this, and you want the second dead. So what's the probability? So they are not independent. So this is without replacement. It means this choosing or selection process is not. Selections are dependent. They're not independent. They're dependent. So if you choose a dead one, so it changes the probability of the second one. So in this case, you have to use conditional probability. So it will be the probability that the first one is dead times probability that the second one is dead, given that the first one is dead. Now, what is the probability that the first one is dead? So it will be 3 over 8, obviously, because we have 3 dead, and in total we have 8 battery. But in the second one, if the first is dead and without replacement, you take it out, and there's the 7 batteries left. So this is 7 batteries left here, because you have the first one at hand. Now the second, in the second, so what's the probability of the second dead? So it was in 8, it was 3 dead and 5 good. Now you choose one dead is gone, and then you have 7, but this time 2 dead and 5 good. So what's the probability that you choose one dead here? It will be 2 over 7. So you write here 2 over 7. So this is equal to 6 over, okay, let's do some simplification. It will be 3 over 28. It will be B then. The back has 3 red marbles and 2 dark blue marbles and 5 light green marbles. You select 2 marbles consecutively. Find the following the probabilities. Now, look at here, this one, getting first blue marble and then a red one, and it says that with the replacement. So this is what's happening is this. So we have 3 red then 2 dark blue, and then 5 green, let's say. Now, then we choose one, okay, 1 marble here, and then with replacement, we mean we do the first row, and then we put it back. So we put it back because it says with replacement. And then you take a second row here. You draw a second ball. Now, since because of the replacement, each draws are independent. So each draws or selection or each draws or selections are independent. So for this reason, you can write this, the probability that the first is blue and the second one is red is equal to the probability the first equal to blue times the probability that the second is red. The first is blue, okay, and so since they're independent, we write the multiplication rule this way, and then when we multiply, okay, what's the probability that it's a blue? So it will be 2 divided by, okay, 3 red, 2 blue, and 5 green, so it makes 10, so it's 2 out of 10 times red. So what's the probability of red? It will be just 3 divided by 10, which is 6 over 100. Now let's look at this one here. There's the getting first one blue and then red one. It's the same question but without replacement. So in this case, each selection or drawing, okay, the selections are depending on each other. So the selections are not independent. So in this case, okay, let's write the same thing. The first is blue and the second one is red. But if they're not independent, this will be equal to the first one is blue, and then multiply with the conditional probability. So the first one is blue, and we're trying to find the second one is red. So the probability that it's blue, okay, it's 2 out of 10. But now it's replaced, okay, one ball taken here, one ball taken. So we end up with 9 balls here in the second one. And which one? It's blue ball taken. So it's the blue, one blue ball taken. So the 9 balls are now 3 red, 1 blue, and 5 green left. So the question is, what's the second is red, so it will be 3 over 9. So it will be 3 over 9, so which is 6 over 19. So 6 over 90, which is 1 over 15. Let A, B be events defined on the same sample space of an experiment such that the probability of A is 0.65 and probability B is 0.4 and the probability of A intersection B is 0.26. So what is the conditional probability here? The conditional probability is equal to the probability of, okay, if we use the rule, what's the rule? Let's remember the rule, it will be the probability of A and B divided by the probability of B. But since they're in the same sample space, you can write here the probability of A intersection B divided by the probability of B. And this will be then A, B, the probability of B is 0.4, and the probability of A intersection B is 0.26. So then you can calculate, you can do the calculation. And the events A and are mutually exclusive or independent events. So this is the question, are they mutually exclusive or independent? So A and B are not mutually exclusive. Not mutually exclusive because if you remember, the mutually exclusive means their intersection is empty set. So this is not the case because it's already given here the probability of A intersection B is not 0. So their intersection cannot be empty set. So are they independent events? Now let's see. If the probability of A intersection B is equal to the probability A times the probability B, then it's independent. So A, B are independent. So let's check if it is like that. The probability of A is 0.65 and the probability of B is 0.4. So this makes 0.26, so it is satisfied. So you can say they're independent. So the correct answer is they're independent. Now, what is the probability of A union B? So we use the addition rule here. It's the probability of A plus the probability of B minus the probability of A intersection B. And the probability of A is 0.75 plus the probability of B is 0.4 and the probability of A intersection B is 0.26, so it has to be 0.105 minus 0.26, which is equal to 0.79, I guess. Yeah, 79. Now, a group consists of equal number of men and women, and of this group, 20% of men and 50% of women are employed. If a person is selected randomly from this group, answer the following questions. So let's find the probability of this person is employed. Now, let's try to uh, okay, let's see the probability that this person is employed. So, but first I want to write all the information here, and I want to use the symbols instead of writing everything. So there are men here. So when you choose a person, this person can be a woman, right? So, or a person is the person is male. So this is male, M, and employed, a person is employed. Now the question is here, the first question is saying, what is the probability that person is employed? Now, let's read the question, and if let's see if something is given about the employment. So it says, of this group, 20% of men and 50% of women are employed. Okay, but it doesn't show directly how much of the population or the group is, how many, what percentage of the group is employed. It doesn't say. But okay, let's put the pieces together. First, let's write what are given here. The first thing is a group consists of equal number of men and women. So what's the probability that we have a person is a man? It's 1/2. And I will just write here not M because I don't want to use more, uh, I don't want to use here more symbols, okay? So it will make it easier. But we can also start with like female. Uh, and here the person can be employed or not. Now 20% of this group, 20% of men are employed. So we can write given men, what's the percentage of men employed? It's, you can write it as a conditional probability. So as I said earlier in the lecture, so this writing is also corresponding to the percentage of the employed people among males. So it will be just 20%. Now 50% of women are employed, it says. So employed, and instead of female, I will just write not M, because I will use the complements here, the complements of the set. So for this reason, I will just use M only. You can start the question, which have no problem. So this will be 50%. Now, by using this information, we will try to get to the probability that a person is employed. So let's remember the Bayes rule. So what does Bayes rule says? The Bayesian rule says if you have A1 and A2 the mutually exclusive and their intersection is empty set, and also the sum of their probabilities is equal to 1, so it means exhaustive. And then you can write the probability of A as the probability of A1 times the probability of E, given that A1 plus the probability of A2 times the probability of E, given that A2. Now the question here is what is an A1 and A2 in this question? What are these in our question? Now the best option seems to be male and not male here, so you can write here choose A1 as male and choose not male. Okay, now you can okay, they're mutually exclusive and they're exhaustive, so we can here write here PE as PE equal to M, the probability E M plus probability A2, which is not M, times the probability E not M. Okay, so what is the probability of males? So this is 1 over 2. Just okay, I will write them here. So the probability of male M times the probability of employed given that male plus the probability of not M, so that means female, times the probability that employed and not male. So this will give you the probability of male is 1 over 2, and the probability that probability of employed given that male is 20%, plus the probability of female not male, it's 1 over 2, and the probability of employed given that it's not male, so this is 50% again. So if you do this calculation at the end, you will get 35%. So the answer here is 35. So when you choose a person with 35% chance he is employed. Okay, if this person is employed, what is the probability that he is male? So I will not erase this part, the information given in the question. Because I will use them again. Now if this person is employed, what's the probability that he's male? So it's asking, this person is employed, so we know, yeah, the person is employed, so it will be a conditional probability. What's the probability that he's a male? So we have to find this, what's the probability of male given that he is employed. So again, we can use the conditional probability rule, the probability of male and employed divided by the probability that he's employed. Now we did this calculation before. This is the probability of being employed. Now the only thing we have to do is the probability of male and employed. So this one, we already know that one from the first part. This is 35%. Now this one here, the probability that the male and employed, you can write this in two ways. One way is to write the probability of employed times the probability of male given that he's employed, or same thing can be written as the probability of employed male times the probability of he's employed given that is male. So this one here, this one is missing. We already trying to find this one, so we will not use this one for sure. So we'll use the second one here, this M and E. So we can use the second formula here. And the second formula, we have the probability the probability of male, which is 1 over 2, and the probability that is employed and given is male. So it's given here, so it's 20%, so it will be 10%. So now we got it, so we can write it here. So this will be now, this will be equal to 35% divided by, no, this is 10%, sorry. It's 10%, it's coming from here and here. And probability of E, it's coming from here, so it will be 35%. So this will be just 10 over 35, and it will be 2 over 7. Now let's try to do the last one. If this person is employed, what's the probability that he is a female? Okay, we don't say he, but we say this person is a female. So it's better we say this person here. Now let's write it. It's a conditional probability again, so we are doing C now. This person is employed. We know this person is employed, and it's asking what's the probability that this person is female, so it means not male. Okay. Now the question is this: how can we find this one? Now we can use the conditional rule here first. The conditional probability rule, it will be the probability of not male and employed divided by the probability of the employed. Now we know that one, this is 35%, and we have to concentrate on the other one, and it's not given here, so we will try to get it by Bayesian rule. The probability of not M and E, okay, you can write this one as, okay, conditional probability, not Bayes, okay, conditional probability, we can use this one, P not M times the probability that the person is employed and given not M. You know, we can change them, but here we have this one, yes, and we have this one here, yes, so we can use that one here. You know, we can switch them, and we can write the formula this way and the other way, but no necessary here because we have all the numbers here, 1 over 2, and this one is 50 over 100, so it will be 25%. And then we can write the probabilities. This is 25%, the first one, and this one is 35%, and this will give you this will give you just 5 over 7. It will be 5 over 7. So this was 2 over 7, I guess. This was 5 over 7, and this is 35 over 100. Now, 3 cable channels, 6 channel 6, channel 8, channel 10 have quiz shows, comedies, and dramas. The number of each is shown here. So these are the channels, and these are the programs, and the number of the totals are here. Okay, if a show is selected at random, find the probability that the show is a quiz show, or it is on channel 8. So it's a quiz show, or it's on channel 8. So here we can write here the probability of quiz. Use the addition rule, the probability of channel 8, and minus the probability that it is a quiz, but in channel 8. on channel 8. So what's the probability that it's a quiz? Um, you can calculate this one, the quiz, the number of total quiz. The total quiz is 8 divided by the total number of programs, it's 31. The channel 8, what's the total 8? Channel 8 total, it's 8 divided by 31. And quiz and channel 8. So quiz, how many quiz programs in channel 8? It's 2, so this has to be 2 over 31. And this will be 14 over 31. So I can say this is 31 over, no, 14 over 31. Now we have the same type question here again. So this is it is comedy, or if you pick a show, this is comedy or drama. And this will be just the probability of that it is comedy, and then drama minus comedy and drama. What's the probability that it's a comedy show? That's comedy show divided by all the shows, the total comedy divided by the total 13 over 1, plus drama. Drama is in total is 10 divided by the total minus comedy and drama. Is there any comedy and drama together? No, they're separate. So this has to be 23 over 31. So I can write here this one, 23 over 31. Now, let's look at this one. The comedy, given the, what's the probability that the show is a comedy, given that it's shown in channel 10? So it says it's a comedy, but we already know it's on channel 10. So if you remember, it's the probability of being comedy and on channel 10. Where is channel 10? Divided by the probability that it's on channel 10. So the comedy and channel 10, it's 8 over 31 divided by on channel 10. This channel 10 is 11 over 31, so which is 8 over 11. So this has to be 8 over 11. Now the other one is, okay, let's do this one. The probability that the show is on channel 6, given that it's a drama. So in this case, we have to look for the conditional probability formula. It has to be, what's the probability that it's a drama and on channel 6 divided by, on channel 6 divided by probability that it's a drama. So if you calculate this one, drama and channel 6, let's check. Drama and channel 6. Drama and channel 6. It's only 4, so we can write here this 4 over 31. Because all TV shows are 31. And what's the probability that it's a drama? So we check the drama total. So 10 over 31. So it will be 10 over 31. So this will give you just 4 over 10. And I think that